1.4 Crystal structure. The ordered three-dimensional arrangement of a particle in a crystal is described using two terms, namely lattice and basis. 1.4.1 Crystal, lattice and basis. Lattice is a geometrical arrangement of points in a three-dimensional periodic array. A crystal structure is obtained by attaching a constituent particle to each of the lattice points. Such constituent particles that are attached to the lattice crystal lattice points from the basis of a crystal lattice. Crystal lattice is also called space lattice of crystal. Thus, crystal is the structure that results by attaching a basis to each of the lattice point. It is represented by the following equation. Table 1.1 Properties of four types of crystalline solids. Property: particle of unit cell. In ionic solid, that is cation and anion. In covalent network solids, that is covalently bonded atoms. In molecular solid, monoatomic or polyatomic molecules. And in metallic solids, metallic ions in a sea of electrons. Second property: interparticle force. Ionic solids, electrostatic. Covalent network solid, covalent bonds. Molecular solid, London dipole forces and or hydrogen bond. Metallic solid, metallic bonds, attraction between cation and mobile valence electron. Third property: hardness. Ionic solids hard and brittle. Covalent network solid very hard. Molecular solids soft, and metallic solids variable from soft to very hard. Fourth property: melting point. Ionic solids high melting point 600 Celsius to 3000 Celsius. Covalent network solids high 1200 degrees Celsius to 4000 degrees Celsius. Molecular solid low minus 272 degrees Celsius to 400 degrees Celsius. Metallic solids wide range minus 39 degrees Celsius to 3400 degrees Celsius. Fifth property: thermal and electrical conductivity. Poor electrical conductors in solid state. Ionic solids poor electrical conductors in solid state, good conductors when melted or dissolved in water. Covalent network solids poor conductor. Exceptions: graphite good conductor of electricity and diamond good conductor of heat. Molecular solids poor conductor of heat and electricity. Metallic solids good conductor of heat and electricity. Unit cell 1.4.2 Unit cell. The space of crystal is built up of three-dimensional basic pattern. The basic pattern is repeated in three dimensions to generate the entire crystal. The smallest repeating structural unit of a crystalline solid is called as a unit cell. When a unit cell are stacked together to generate the crystal, each unit cell shares its faces edges and corners with neighboring unit cells. It is important to understand that the geometric shape of a unit cell is same at that of macroscopic crystal. For example, if the crystal has cubic shape, the unit cell will also have its constituent particles arrangement to form a tiny cube. The three dimensional the dimensions of unit cell along the three edges are denoted by the symbols a, small b, and small c. The angles between these axes are represented by symbols alpha, beta, and gamma as shown in figure 1.1. 1.4.3 Types of unit cell. There are four types of unit cell. First, primitive or simple unit cell. In primitive unit cell, the constituent particles are present at its corner only. Body centered unit cell. In this type of unit cell, one constituent particle is present at the center of its body in addition to the corner particles. Third, face centered unit cell. The unit cell consists particles at the center of each of the faces in addition to the corner particles. Fourth, base centered unit cell. This unit cell consists of particles at the center of any two of its opposite faces in addition to the corner particles. 1.4.4 Crystal system. By mathematical analysis, it has been proved that only 14 different kinds of space lattice are possible. In other words, there are only 14 ways in which similar point can be arranged in a three-dimensional order. These 14 lattices, which describe the crystal structure, are called Bravais lattice. 14 Bravais lattices are divided into 7 crystal systems. The possible combination of lattice point spacing small b, and c along three edges and the angles alpha, beta, and gamma between these axes